Hello students. So in our today's video, we would be covering capacitor practice problems. Okay. So we would practice numerical problems on capacitor, and this is the fourth lecture in the capacitor series. So if you have not gone through the previous one, I would urge you to go through the previous videos on this same series, and you can just go to the playlist provided with this link, and you can go to the other ones. And but in today's class, our prime focus would be to look into different problems related to capacitors. So fundamentally, if you are writing an entrance exam, or even if you are preparing for a board exam, you may expect numericals related to capacitors. So in exam, you may get a geometry of capacitors, and you may be asked to find out the equivalent capacitance. Similarly, there could be some other tricky problems which we would see in due course of our today's class. So let's get started, students. So before we start, just one quick recap of our basic formula of capacitors, right? So or related to series and parallel. So first thing is, we know two two capacitors are said to be in series when at their connection point, there are two and only two of them. The moment you see a third capacitor, okay, and I'm assuming that we are talking about a closed circuit. The moment you see a third capacitor connected at the junction point, they are no more in series, and I call it out with Rajiv's lover couples law. So we have seen it in registers. The same rule will apply for capacitors as well. Coming to parallel combinations, we know that two capacitors are said to be in parallel if taking those two if taking two and only two capacitors, we can complete one loop, then we say they are in parallel. And I repeat, these are tricks to solve problems. You should not be writing it as a theory or a definition of series and parallel. For definition of series parallel, we know the classical rules, right? That if two capacitors are connected in a way that the charge appearing across their plates are same, they are said to be in series. And when the potential difference appearing across the ends of the capacitors are same, then we say that they are in parallel. So that is the theoretical definition, and practically we would use these two definitions. Also, we had seen that when capacitors are in series, the C equivalent of two capacitors would be C1, C2 by C1 plus C2. So if you see, this is just opposite of resistors. So when resistances are in parallel, the equivalent resistance becomes R1, R2 by R1 plus R2. In case of capacitor, it's just the opposite. Okay. Next, when it comes to parallel, so C equivalent would be obviously C1 plus C2. So that's why I repeat, students, the equivalent capacitance formula or the equivalent capacitance and equivalence resistance formula are always reciprocal. So yeah, the formula for parallel will be equal to series, and series will be equal to parallel when you compare your series, and when you compare your resistances and your capacitances. Okay, now let's move on to our today's set of problems, and let's solve them one by one. Okay, so let's get started with a pretty simple one related to geometry. So we would start with a geometrical combination. So say we have a triangular shape where we have one capacitor here, that is 4 microfarad. We have one more here, again 4 microfarad. Okay. Say we have one here, that is 1 microfarad, and the triangle is complete, but our circuit is not complete. We want to make it little more complex. So we'll add one more capacitor here, say 3 microfarad. I'll add one more capacitor here, 3 microfarad, okay? And I'm asking, find out the equivalence capacitance across points A and B. So we want to find out the equivalence capacitance across points A and B. So we'll go step by step. So let's just give some notation to all the capacitors for easy recognition. So say we call it capacitance 1, 2, 3, 4, and 5. Okay. And as we know, we try to see whether capacitors are in series and parallel, always in a pair of two. Okay. So if you see here, between capacitor number 4 and 3, between capacitor 4 and 3, this is the junction point, right? But if you observe, can I say that 4 is in series with 3? The answer is no, because at this junction point, yes, it's right that 4 and 3 are connected, but if you see, 1 is a disturbing element here. So 4 and 3 cannot be a happy lovers couple. So 1 is a disturbing element, so it's troubling their relationship. So obviously they are not in series. Okay. Similarly, if you see 5 and 3, same thing. So 5 and 3 are connected here, but 2 is a disturbing element, so obviously they would not be in series as well. And if you take 2 and 3, same thing. When 2 and 3 are there, this is the junction point or connecting point, and this capacitor number 5, this is a disturbing element. So obviously between your 3, 4, 5, these are not series with each other, nor they are in series with one or two. So it's not possible in that way. But if you notice between 1 and 2, between 1 and 2, this is the junction point, and at the junction point, if you see, there are two and only two capacitors are there. So obviously, I can say that one is in series with two. So which law we are applying? We are applying our, your Lover's couple law. That, at the junction point, if there are two and only two resistors, there is no third disturbing element, then obviously we say that they are in series. If one is in series with two, then what would be the equivalence capacitance? So we know two capacitors whose capacitance are same and they are in series, so equivalence capacitance here will be C by 2. So that is nothing but 4 by 2 equal to 2 microfarad, right? So if one is in series with 2 and the equivalence capacitance is 2 microfarad, so obviously I can remove both of these, and in place of both of these, I can connect one 2 microfarad capacitor, right? So rest all drawing remains same. So now this is a 2 microfarad capacitor. Okay. Now if you see between this 2 microfarad and capacitor number 3, okay, by taking these and only these two, I can complete a loop. If you see here, by taking these and only these two, I can complete a loop, which means they are a happy married couple, which means they are parallel. So I can say that this 3 microfarad capacitor is in parallel with my 1 microfarad capacitor. So obviously your C equivalent would be the summation of both of these. So your C equivalent will be C1 plus C2. That is nothing but your 2 plus 1 here. So 3 is just the name that I given to the capacitor. Okay, the capacitance is 1 microfarad. So 2 plus 1 obviously will be your 3 microfarad. So which obviously means that I can remove both of these, and in place of them, I can just put one 3 microfarad capacitor. So this capacitor now would be 3 microfarad. Now if you notice, now the circuit has become very, very simple, where 4 and this 3 microfarad. See, obviously they are in series because this is the junction point And at the junction point, there are two and only two capacitors. There's no third disturbing element. So obviously, your four or your one your 3 microfarad capacitor, 3 microfarad is in series with the 3 microfarad. And if you see, this one is also series with this microfarad, series with 3 microfarad. Again, the reason is same. This is junction point. At the junction point, there are two and only two elements. There is no third disturbing elements. So when all three of them are in series, so your C equivalent would be C by N. So N number of capacitors connected in series, all having a capacitance C. So C equivalent is obviously C by N. So that is nothing but 3 by 3 or 1 microfarad. So the answer is the if you arrange capacitors like this, the net capacitance, the C equivalent that you will get, that will be only 1 microfarad. Okay, so if you notice here one thing, if we want to increase capacitance, right, in a circuit, obviously we look forward to, keep the capacitors in parallel. Okay, and for some reason, if we want to decrease the capacitance, we look forward to connect them in series. Sometimes you may get a problem that these many capacitors of this capacitance are given to you. Arrange them in such a way to get a C equivalent of this one. So sometimes you get even a problem like that. Okay, so you can solve that as well. Okay, now now if we are done with this, now let us look into a couple of interesting problems here. We will do slight change in the geometry that we saw in problem number one, and then let's see how would it change things. Okay, okay. So yeah, we will just go with the same geometry and we will slightly modify one or two things. So here we had one microfarad capacitor. Okay, so here we had one 4 microfarad. We had one more 4 microfarad like this, 4 microfarad, 4 microfarad, 1 microfarad. Suppose now I connect one more 4 microfarad here like this, right? And if I want to know, suppose across the same 2 points A and B, I have 1, 2, 3, 4, 5, and 6 capacitors. Okay, and I want to know what is the equivalence capacitance. So if you see here, the sixth capacitor that I connected, the other end of that is not closed, not closed. So obviously, in an electrical circuit, if you are not closing your loop, right? So obviously, there would be no, what you say, charge distribution because of that. So just imagine if you just buy a capacitor from market, okay? So say you went to market, you bought a capacitor of capacitance, maybe suppose your 10 microfarad capacity, but until and unless you have charged it, right? Obviously, it does not have any effective capacitance to be, and obviously it cannot dissipate any charge to the electrical circuit that it is connected. So that's why first a capacitor absorbs charge, right? It stores charge in the form of electrical energy, then it dissipates to the circuit. So that's why, obviously, if there could be no charge distribution, this capacitor is useless for the circuit. So remember, students, if a capacitor is not closed at all, if that part of the circuit is not closed, you can happily remove that wing. Okay, so obviously for that reason you can remove it, and once you remove it, this becomes same to your previous problem. Okay, so you can take it down as practice problem number two, where we have connected one external capacitor here, and we were trying to see what is the equivalent capacitance, and the answer is obviously as it is not closed loop, so we can remove it and nothing changes. Okay. Okay, now let's change the problem slightly. Okay, so say now between these 2 points, okay, so say between these points P and Q and R, I will play some magic, okay. So between point P and Q, if I connect a wire, practice problem number 3. I have connected a plain wire between points P and Q across the second capacitor of 4 microfarad capacitance. And now I'm asking, what is the C equivalent of this circuit? Okay, so quite simple, students. Just go through the same concept which we just talked few minutes back. If a particular limb of a circuit cannot contribute to charge distribution, obviously that limb is useless. So that's why, if you notice here, this this conducting wire has provided a short circuit path. Okay, so just like in your registers we had done, if a particular register is short circuited, then you can disconnect it from the entire circuit. Okay, so see, between point P and Q, when you have a complete resistance less connection, so this is how we do not denote the short circuit path, right? So the moment you get a no resistance path, obviously entire charge will flow through this and no charge will flow through this limb. If this capacitor gets no charge, obviously it's a useless capacitor in this circuit, which means you can happily remove it. So let's remove it. Okay, so it is just there to show you as an illusion and create confusion to you. So remove this capacitor. Now once you remove this capacitor, then if you see, the problems become slightly different. Okay, now between this your 4 microfarad capacitor and 1 microfarad capacitor, if you see, they are now in parallel, because go with the second rule that we have established, taking two and only two capacitors. If you can complete a loop, then they are a happy married couple, happy married couple, and obviously we say that they are in parallel. So here I'll say your 4 microfarad capacitor is in parallel with 1 microfarad capacitor. So obviously your C equivalent will be C1 plus C2. It is nothing but 4 plus 1. That is nothing but 5 microfarad. Okay. Now, so obviously, which means I can remove all these and I can put one 5 microfarad capacitor in place of this entire combination. So I'll put 5 microfarad here. Now, if this is 5 microfarad, then obviously if you see, now this is in series with this 3 microfarad, this is in series with this 3 microfarad. Okay, now we have 3 capacitors, all are in series. So let us use the formula. 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So obviously this will be 1 by C equivalent is 1 by 3 plus 1 by 5 plus 1 by 3. So obviously your LCM will become 15, and here it will be 5 plus 3 plus 5. So that is nothing but 13 by 15, or your C equivalent would be 15 by 13 microfarad. That's the answer. Okay, so if you notice here, how, if one particular limb is short circuited, that obviously would impact to your overall capacitance, and the limb that is across that short circuited path, there would be no charge distribution, and obviously you can remove it from the circuit, and obviously that would make your circuit much simpler, right? So good. So let's move on to the next practice problem. Okay. So the only trick here was, your how to remove the limb that was short circuited. Okay, and everything else is simple math. The only trick was related to your identifying the short circuited path. Okay. Now let's look into a different problem. So let's go into uh, the next problem, and this is we say your capacitors connected in the symmetry of a ladder. Okay. So this is say your point A. We have one capacitor here, one more capacitor here, and this is point B. Okay, we are repeating this series few times. Okay, again we'll repeat it here. Okay, and the numbers that we want to repeat them with is, okay, so this is 4 microfarad, this is 4 microfarad. Okay, this is 2 microfarad. Okay, all the ones in this side, we are taking them as 4 microfarad, 4 microfarad, 4 microfarad, 2 microfarad, 2 microfarad. Okay, so if we are given a circuit like this, right? So again, first thing, let us just do a bit of numbering. Okay, so let's start from here. So say, and again, numbering you can give it in any way you want. There is no hard and fast rule. I'm just giving it for nomenclature. So capacitor number one, capacitor number two, three, four, five, six. Okay, and now let's see. So if you see, quite simple that between one, two, and three, you cannot say which one are in series or parallel directly. Similarly, between three, four, and two, it's not possible. Okay, but if you see between your capacitors five and six, I can say 5 is in series with 6. Simple reason. This is the junction point. At the junction point, there are two and only two capacitors. So they are a happy, lovers couple. So 5 is in series with 2, which means the equivalence capacitance would be 4 by 2, that is nothing but 2 microfarad. Okay. And we know once we find out equivalence capacitance, we can remove those two capacitors, and in place of them we can just put one capacitor. So let me put it like this. Okay, so say now the circuit would reduce to something like this. So rather than saying 5 and 6, now this will be 1 2 microfarad capacitor. Okay, now if you see, this 2 microfarad capacitor is in parallel with capacitance number 4. So this 2 microfarad capacitor is parallel with capacitor number 4. Why? Simple reason. Just take these two, and if you see here, you can easily complete one loop. So taking two capacitors, if you can complete a loop, then we say that they are parallel to each other. So if they are parallel to each other, so the equivalence capacitance would be C1 plus C2, that is nothing but 2 plus 2, that is 4 microfarad. Now, if equivalence capacitance is 4 microfarad, obviously I can erase both of them, and in their place, I can just put their equivalence capacitance, that is 4 microfarad, right? So here it will become your 4 microfarad. So similarly, if you see, this 4 is in series with this 4, so obviously it will be 4 by 2 equal to 2 microfarad. Now I'll erase both of them, and in place of that, I will just write 2 microfarad. Okay. Now similarly, this 2 microfarad is parallel with this 2 microfarad, so which means across the same 2 points, right? I'll erase both of them, and I'll just write 4 microfarad, because both of them are in parallel, so capacitance gets added, so the equivalence capacitance becomes 4 microfarad. Now if you see, this 4 microfarad is in series with our first capacitor, 4 microfarad, because now this is the junction point, and you don't have any other disturbing element. You may think that, sir, initially we had so many. Yes, but when we are solving, So obviously we are substituting by the equivalence capacitance. So obviously we can say that the other ones are not there. Okay. So now it would be 4 microfarad capacitor is in series with other 4 microfarad capacitor. So obviously your C equivalent will be 4 by 2, that is 2 microfarad. That's the answer. So if you see, sometimes your circuits may look big, but they are predominantly just to create an illusion. And the moment you apply these rules, obviously, they would shrink like, a lid shrinks when you apply salt to it, right? So that is how easy they are. Okay, fair enough. So if you want to take down any note on that, go ahead. And in the meanwhile, I'll drink a bit of water and then we'll go on to our next practice problem. Okay, let's keep moving. Let's go to our next practice problem where we will just make this thing a little more complicated. Okay, so what we are gonna do is this problem is quite famously known as your infinite ladder. Infinite ladder. Okay, infinite ladder. So the same ladder, if we had suppose infinite loops, then what would have happened? So let's take the same thing. So you have point A, this is 4 farad, sorry, 4 microfarad, this one is 2 microfarad, this is your point B. So here you have another 4 microfarad, here you have another 2 microfarad. Try to ensure that the length of both these bars are same. Obviously, it will look like a cell, okay? Because in cell you have your positive terminal denoted as a larger line and negative terminal as a smaller line, but capacitors it's same. Okay, so yeah, and say like this, we had n number of loops, okay, and finally you have one 4 microfarad, one suppose your another suppose your 2 microfarad here. So that is how this is repeated to till the end. Okay. So if it is repeated like this till the end, if it's an infinite ladder, okay. So if the same ladder is repeated n number of times or infinite number of times, then how do we find it? Okay. So here we'll use one small trick. Okay. So assume all these are 4, 2, 4, 2, 4, 2, like that. Okay. So you have your suppose n number of loops. Okay. Now if there are your infinite or not n, let's say your infinite number of loops in this ladder, then how do we find it? So we use a small trick here. Okay, so we'll just draw an equivalent capacitance of it. Okay, now tell me students, infinite plus 1, infinite minus 1. Okay, so can I say that infinite plus 1 equals to infinite? And I know that when it comes to absolute mathematics, all these mathematical operations with infinite are undefined. But if you say limit x tends to infinite, then I can say infinite plus 1 is infinite, right? So say if you have a very huge ocean, you just put one jug of water into it. So obviously the water level of ocean doesn't change. Similarly, from an infinite ocean, if you take out one jug of water, obviously the water level of the ocean does not go down, right? So that is why we are saying that infinite plus 1 can be safely assumed as infinite. Infinite minus 1 can also be safely assumed that is infinite. Okay, so the reason why we are doing is, can I say that in this entire your loop, okay, so let me do one thing. Let me just leave out the first one. Okay, so here I have one 4 microfarad capacitor. Okay, I have one 2 microfarad capacitor. Okay, this is A, this is point B. So after this, if I leave this, right, so can I say that this will still be an infinite ladder, right? So I can say that now this is an infinite ladder, and I want to find out, obviously, the capacitance of this infinite ladder. Okay, okay. So if you see here, okay, so suppose this is your C, this is your 2, this is your 4, and we want to find it out. Okay, now the trick is I have just left the first loop of the ladder, and then I have taken taken the rest of it. So obviously infinite minus 1 is infinite, so this itself is an infinite loop. Now I have put this equivalence capacitance as C equivalent. This one is 4 microfarad, this one is 2 microfarad. So if you see here, obviously your C equivalent and 2, these are in parallel, because your by taking these two and only these two, you can complete one loop. So equivalence capacitance of these two together would be C equivalent plus 2, right? We know the simple rule for your parallel. Okay. Similarly, when we see this one and 4, they are in series. So obviously the capacitance of this one and 4 would be C equivalent plus 2 into 4 by C equivalent plus 2 plus 4, C1 into C2 by C1 plus C2, same formula. So let's uh, try to solve it. So what do we get? So this is nothing but 4 C equivalent plus 8 by C equivalent plus 6. Okay. Now, if this is the value I'm getting, so obviously this is the value of my your infinite ladder capacitor. So obviously I can say that this entire thing is equal to your C equivalent. So C equivalent can be written as 4 C equivalent plus 8 by C equivalent plus 6. Okay. Now, obviously, I need to do a bit of maths here. So here I'll say, I'll take this thing on this side and multiply this with this. So I get C equivalent squared, okay, plus 6 C equivalent, okay, equal to 4 C equivalent plus 8. Okay, for simplicity, let me just put C in place of C equivalent. So can I say that this is C square plus 6C equal to 4C plus 8. Now let me bring everything to one side, so this becomes C square minus, sorry, plus 2C plus, sorry, your minus 8 equal to 0. So if you see, this is a quadratic equation of the form ax squared plus bx plus c. So if it's a quadratic equation, obviously I can find the roots of this quadratic equation like by using this formula. So we know in a quadratic equation, the root is nothing but minus b plus minus root over of b squared minus 4ac by 2a. So obviously your capacitance C will be nothing but what is the value of minus b? So this is ax squared plus bx plus c. So obviously your a is 1, bx squared. So b is 2 and c is minus 8, right? So we'll just replace it here, and we can get the answer. So that is nothing but b c equal to minus b. Minus b is nothing but minus 2. Okay, plus b square minus 4ac. B square, that is 4, minus 4 into a. A is 1. C is how much? Minus 8. B square minus 4ac root over by 2 into, what is the value of a? A is again 1. Okay, so which would be nothing but minus 2 plus, this is 4 minus of minus is nothing but plus 4 plus, this is 8 4 is 32 root over by 2. So obviously this becomes root over of 36 is nothing but 6. So 6 minus 2 is 4. 4 by 2, that is nothing but 2. Okay. Similarly, if you put minus here, if you put minus here, then this entire term will be how much? Minus 2 minus this is root over of 36 is nothing but 6. So that is minus 6 by 2. So equivalence capacitance will be minus 8 by 2, that is minus 4. So which is obviously not a valid answer, because capacitance does not, you would not get it in the minus. Oh, looks like this bottom part you could not see. I'm sorry about that. So obviously it's a simple math, right? So here we are getting capacitance as 2, the other value that we are getting is minus 4. The minus 4 value is not acceptable. So your answer would be 2. So if you are creating an infinite ladder, then you can obviously use this trick. And here we are using the formula for quadratic equation. Okay. If you want, you can also use your middle term your middle term splitting, and you can factorize this quadratic equation and solve it for both the roots. That's also possible. So I just chose the easier one. I just because I am not practicing maths problem here. I just want to know the root of it. So I just applied the formula and I got the value of C equivalent. Okay. So if you want, you can just note it down. And as usual, let me give a bit of water in the meantime. Okay. So now let's move on to the next problem. Okay. And this next problem is again related to symmetry. So if you see, we solved couple of problems related to your series parallel symmetry. We solved for your open circuit. We solved for short circuit. We solved for ladder and infinite ladder. Let us see one or two more problems related to symmetry. Okay, so we'll see just one problem related to symmetry, and there's a reason behind it. I'll tell you as soon as we are done with that. Okay, so say, yeah, let's get into this problem. So say this is the geometry. You have a triangle like this. We have three capacitors, all having capacitance C connected here. We have one more node here, like this, like this, like this. We have one more node like this. Okay, and then it has asked find out what is the equivalence capacitance across points A and B, given capacitance of each capacitor is C. Okay, so capacitance of each capacitor is C, and it's asking what is the value of the C equivalent capacitance. Okay, so if you note, and again, step number one, give some name 1, 2, 3, 4, 5, 6, 7. Okay, somebody wants to start naming from this side. Obviously, your choice. As I said, there is no hard and fast rule. I'm just giving it for my own nomenclature. Okay, now if you see here, we had solved a similar problem related to registers. So in registers, we had solved this problem, right? Okay, and here there was one register, here there was one more register, here there was few more registers like this, and we had solved the equivalence resistance across this. Okay, so remember students, when it comes I mean, personally, I feel, and concept-wise also, it's relatively easier to solve when have capacitors. And remember, we know that the series parallel rule of capacitors and resistors are just opposite to each other. So in an entrance exam, if you are getting capacitors like this, and you feel that, you may be confused, because when we have capacitors connected in a circuit, obviously there is no proper flow of current. Okay, so the entire gamut is by charge distribution. So that is why sometimes it becomes a little difficult to realize your open circuit, closed circuit, symmetry and all. okay, and how current will get distributed, because there'll ideally be no flow of current. It may be just for a split up movement for the capacitors to get charged, and that's it, right? After that, so that's why I personally would recommend, if you're getting a problem like this related to capacitors, draw an equivalent, circuit in resistors, find out whatever is the equivalent resistance, okay? So suppose your R equivalent is this. What are you find the R equivalent? Suppose you find, X by Y R, assuming capacitance of each resistance is R, and you have X and Y are two numbers where Y is not equal to 0. If you are finding R equivalent equals to X by Y R, obviously your C equivalent will be Y by XC. Blindly, you can just, reverse it. If it's, so if it is equivalent resistance is 3 by 5 R, the equivalence capacitance will be 5 by 3C. If it is 100 by 379 R, then obviously it will be 379 by 100 C. Okay, so capacitance and resistance will always you will get, reverse numerics. And again, this will work for an entrance exam. Okay, now if suppose you get it in a board exam, how should you solve it? Okay, so let's look into that. Okay, so just follow a very simple principle that similar to your electrical circuit. Okay, so when you get like this, okay, you should mentally connect this circuit to an electric cell. Okay, mentally connect this circuit to an electric cell. Now if you connect it to an electric cell, the first and foremost thing is we need to find out charge distribution, charge distribution across across each capacitor. Okay, we'll find out charge distribution across each capacitor. Okay, and then the next thing is any limb which is either an open circuit or a closed circuit, okay, we'll remove it. Okay, so say let us send, a plus q charge from the positive terminal of the battery and a minus q charge from the negative terminal of the battery. So so this end of your three, your capacitor number three, suppose, so if you see charge q is coming up to here, and here it will get divided. Okay, so say here this part is getting charge q1 and this part is getting charge q2, right? So when you go from the negative side, so here this part will get minus q2, okay, and this part will get minus q1. That's why we say these problems are symmetry problems. So if you are sending q1 here and plus q2 here, send minus q1 and minus q2, in the symmetrically opposite directions. Okay, now if charge on this plate is the charge on this plate of capacitor 1 is q1, obviously the charge induced on this other plate will be minus q1. Okay, here if charge induced is plus q2, here it will be minus q2. If it is minus q2 here, it will be plus q2 here. If it is minus q1 here, it will be plus q1 here. Okay, now we reach this point. Again, if you see, there are, charge can go to this side, charge can come to this side, right? So say some your q3 appears here. Okay, so now this is minus q1. So if it is minus, so the other plates which are connected to this, so we know that this plate, and this plate, they are forming an isolated system. In an isolated system, the net charge is always zero. So if there's a negative charge here, then obviously some positive charge Q3 and Q4 will appear here, such that your Q3 plus Q4, okay, will be equal to Q1, right? Because this is negative, this is positive, equal in magnitude, opposite in sign. Okay, that much charge distribution will be there. Similarly, if we are going from this side, right? So if minus q1 is here, plus q1, if this is plus q1, if this is plus q1, then obviously here and here it will be minus. Okay, and obviously if here it is plus q3, here it will be minus Q3, and here it will be your minus Q4. If it is minus Q4 here, it will be plus Q4 here. Okay, and if it is plus Q4 here, then it will be your minus Q4 here. If you notice here, your charge minus Q4 is here, plus Q4 is here. So which obviously mean I can redraw it like this, right? That the entire charge here is, minus Q4 plus Q4, that is 0. So which means in this limb, if you see this small limb, actually no charge is getting, distributed here. If no charge is getting distributed, I can disconnect it just like we saw in your, short circuit thing. Now, if you see, this is now very simple. These two are in series, that is in parallel with this. So C and C series, this is C by 2. C by 2 in series, that is parallel with C. So C by 2 plus C, that is nothing but 3C by 2. Okay, so I can remove this entire thing that is in this side, and I can place, oh sorry, this one will not be removed. This one is 3C by 2. Now 3C by 2, C and C, these all are in series. So your CC series, C by 2, C by 2 and 3C by 2, they are also in series. So obviously 1 by C equivalent of these three is nothing but this one is C, so this is 1 by C plus 2 by 3C plus 1 by C. So LCM is 3C. So this becomes 3 plus 2 plus 3. That is nothing but how much? This is 8 by 3C, or C equivalent is 3C by 8. So I can remove all these, and in place of all these, I can write 3C by 8. 3C by 8. Now, this C and this C are in series, right? Because this is a junction point, there is no disturbance, so there can be a happy lovers couple. These are in series, so which means I can remove both of these, and I can put one C by 2 here, right? So this is C by 2, this is 3C by 8. These are in parallel. So obviously the equivalent capacitance will get added. So it will be 3C by 8 plus C by 2. LCM is 8. This is 3C plus this is 4C, right? So obviously this is 7C by 8. Okay. So if you want to do an experiment, just replace all the capacitors with your resistors, and if you put all the resistors, then your R equivalent will be 8R by 7. So that's why I say, if anytime you feel that you are getting confused in the charge distribution, and you are more comfortable in the current distribution of resistors, I recommend from an entrance exam perspective, solve it for resistors, find out whatever is the R equivalent, and just take a reciprocal of it. Okay, so 1 by whatever you have got, that will be the C equivalent. Okay, fair enough. Let's if there is no confusion, let us move into a different one. Okay, so it looks like we may have to push the your unbalanced Wheatstone bridge for the next class. So honestly, it would be a pretty heavy session. Okay, we'll see one or two different problems here today. Okay, so let's look into that. Okay, so this problem again is on. Okay, so let's move on to this. So this problem is again on a bit of your restructuring. So in resistors and series, in resistors and capacitors, when you get circuits, many times you may need to redraw the circuit to to arrive at your solution. And this is a pretty nice and classical example of it. Okay, so let us see. So say here you have one plate, here you have another plate. This is the positive plate. Okay, this is the positive plate. This is your negative plate. And the way things are arranged are, okay, so say, okay, so here, this is another capacitor. So one positive plate, one negative plate, separated by a small distance d. Obviously, they would form a parallel plate capacitor, right? So here you have another negative plate, which is connected to this. You have another positive plate connected to this. You have another negative plate connected to this. You have another positive plate connected to this. You have another negative plate connected to this. Okay, so it's given that capacitance of this first capacitor is C1, capacitance of your second capacitor is C2. And again, these are not connected. Okay, I'm just letting you know. Okay, so this capacitance of this one is C1, capacitance of this one is C2, capacitance of this one is your C3, capacitance of this last one is your C4. So four capacitors if they're connected like this. Okay, so if you notice here a little closely, right? All the positive terminals of all these capacitors are connected. Okay, and if you see, all the negative terminals of the capacitors are also connected. So if you remember, in parallel combination of capacitors, we know that suppose there are n number of capacitors connected like this, right? So we know that all their positive terminals are connected, all their negative terminals are connected, and obviously the potential difference across all of them are same. That is when they become parallel to each other. So if you see here, this is exactly the same case. Okay, so when it is asking you to find out the equivalence capacitance, obviously across these 2 points, right? So if we if we know that we need to mentally connect a cell to it, right? So I have connected a cell to it mentally, and I would suppose send charge plus q from here and charge minus q from here. So if you see this charge plus q which is coming, obviously that would be equally divided on all these positive charges, all these positive plates. You have four positive plates. So obviously, say here you will get q by 4, here you will get suppose q by 4, here you will get q by 4, here you will get q by 4. And obviously, the induction on the negative would be minus q by 4, minus q by 4, minus q by 4, minus q by 4, which very quickly or very easily indicates that these four are in parallel. And if four capacitors are in parallel, so obviously your C equivalent will be C1 plus C2 plus C3 plus C4. So sometimes what happens, it would intentionally give you a circuit which may look difficult, but in reality it's not difficult. So if you see, it may look a little difficult, but the moment we notice that all the positive terminals are connected, all the negative terminals are connected together, and the charge appearing across them is same, which means your potential difference appearing across each of them is same, right? Because these are connected to the same. So if you see, these are actually connected to the same terminals of the cell. Okay. Oh, sorry. I mean, the charges may not be q by 4 in all the places, but as they are connected to the same terminal of the battery, right? So if potential here is V, okay. So obviously all the your positive terminals that are connected to this will have a potential V. And here, if it is, suppose it is your zero, because most of the times we say that the negative end is at zero potential, okay? Because potential is always a point function, okay? So we'll say that the potential difference across all the capacitors are obviously the same. So if the potential differences are same, then these capacitors are in parallel. And if they are in parallel, obviously the equivalence capacitance would be C1 plus C2 plus C3 plus C4. Okay, so that is how we will be able to solve it pretty easily. Okay, so we will see, we will take a pause here for this class, and in the next class we would say we know that in the definition of capacitors we have studied that two plates of equal area when separated by a small distance, and both of them are given charge, same charge. One is given charge plus q, obviously the charge induced on the other one is minus q. That forms a capacitor. But do we think that, what would happen if both the plates are given different charge, which means maybe they are connected to different cells, and then they are receiving different charges, amount of charge from different sources of charge. In that scenario, does that form a capacitor? If yes, then what happens? If no, then what happens? All these and problems related to Wheatstone bridge and dielectric in the next class. Stay tuned, and we'll catch up in the next class. Thank you, students.